this computer. Okay, so today we're going to continue our exploration of MRI. And what we're going to do is we're going to sort of wrap up sort of the imaging part, which is how do you make the images. We'll review a little bit of what we talked about last time, and then we'll get into compressed sensing and deep learning, which are really pretty novel, but sort of now almost standard on systems. And then we're going to switch gears and get into sort of more getting back into sort of almost the rest of the course will be more on like how do we actually apply MRI to look at physiology, anatomy, and what do the images mean, and what's the interesting information we can get out. Before I start, so yeah, so the proposals, I started looking at them. They look really good. So basically what I'm doing is I'm using Gradescope and I'm gonna give comments, and if it looks good, you just get 1 point and then you're done, and just post everything on the Google Sheet. If it needs sort of revision, it's like, oh, maybe you need to do it again, then you'll just have to resubmit it until it's sort of got enough, until I think that the project proposal is sort of going to be beneficial to you. All right. Okay. And then in terms of the pre-lecture quizzes, I think everyone did really well. I think the thing to remember is just remember these sort of, these things like delta kx has to be less than a certain number, whereas wkx has to be greater than a certain number. So the sort of greater and less than is sort of important to keep in mind. And then the other question is sort of, I think, there's a question of how the G max is for this maximum. Okay. And that only takes you about halfway to K space, to like minus, this takes you out to like minus KY max. Okay. And so I think some people sort of did the whole width, and so that would give you a different answer. And so those are some of the issues that people had, but most people did really well. So that's good. Okay, so let's just talk about where we were last time. So last time we sort of covered these three things, and we'll review those really quickly. And so these are in the realm of parallel imaging. And this is where you're still actually trying to create an image based on just the data you have alone, okay? And so we'll review those really quickly. And then this, we found out it's useful to have like a linear algebra point of view, because you're just essentially solving either overdetermined or undetermined systems. And if it's underdetermined, you're trying to make it overdetermined, right? And today we'll cover compressed sensing and deep learning. So we'll cover these two. And these are sort of a paradigm shift in the sense that and then this simultaneous is also a type of parallel imaging. So these are all sort of parallel imaging. But today we're going to sort of move into compressed sensing and deep learning, which is a sort of different paradigm, which we're going to talk about, which is basically more of a probabilistic point of view of saying that you should be just like LLMs make use of a lot of information. There's a lot of information about images, and so you should make use of that. And if you don't, you're sort of not having a good enough prior on your data. Okay, so just to remind you where you're at, and sort of if you're still working on the homework assignment, just to remind you what we're trying to do, which is pretty much the first 4 lectures or so, we're talking about all this stuff. How do you go from a Fourier transform back to the signal, and how do you sample this Fourier transform sufficiently so your image looks good? Okay. And then last time we talked about how, this sort of going back and forth between the signal and the object can be written as a sort of a linear system of equations where this is what we measure. This is the encoding matrix, and this is the image we want. Okay. And so I think everyone's sort of seen this sort of before, where you basically now you try to invert. If you want to solve for the image, essentially you're solving for the image. And so the best case scenario is that this is invertible. All right. And if the encoding matrix represents a Fourier transform, then the inversion is very simple. It's just the inverse Fourier transform. So that's nice. All right. Oops. And the key is that we take these 2D images and we vectorize them so that we can use MATLAB or any linear algebra solver to solve it. Okay. So the Fourier solution is this one. Okay. So that's the Fourier solution. If E is invertible, which also tends to mean you've satisfied the Nyquist criterion and everything else, then E will be invertible and you're set to go. We also looked at what happens if you have more equations than unknowns, and there you can have a solution, but it's going to be what you call your least squares solution. Okay. It's not going to exactly solve these, but it's going to be S is going to be approximately equal to EM, where the error is minimized. Okay, so that's the least square solution. And we also talked about underdetermined, where now this is like where you haven't satisfied Nyquist, right? You don't have enough samples. And so therefore, this is what we led to aliasing. Okay. And so the trick behind parallel imaging we talked about is to go from something that's aliased to make it something that's um, overdetermined. So now we can solve it. All right. So that's sort of reviewing what we did. And the real key to sort of making all this work is the fact that we have different coils. Okay. And it sort of makes sense. Basically, previously we're counting on the Fourier transform to do all the work. We're saying like, here's an object, the Fourier transform, you've got to sample it and you've got to go out far enough k-space. You got to figure out everything. But if you think about if you had a bunch of coils on someone's head, like I put a coil here, it's going to be sensitive to this part of my head. Another coil here is sensitive to this part of my head. That should tell you something about your object too, right? For example, if there's nothing here, this coil is not going to pick up anything. So these coils have a lot of information, and if you don't take into that account, you're sort of throwing away information. Okay. So the main thing was how to use the coils to introduce more information. And so the first case where is you actually have a bunch of these coils and you're not trying to go faster or anything. You're just saying, well, how should I combine these coils? And so this leads to this overdetermined system of equations where each of these is telling you the coil sensitivity. Okay, these are the coil sensitivities. And so they're actually telling you something about like if a certain coil doesn't see anything, then it means that there must not be any signal that close to it. Okay. And it turned out the solution is very simple. It's the sum of squares where here coil one sees something, here coil two sees something. I just take each one of those, I take the magnitude and square it, and then I sum them up and take the square root, and I get a pretty good looking image. Okay, so that's sort of, if you didn't really want to go faster, this is how you should combine the data. All right. But let's say in general, we want to go faster. Okay. And some of your projects will look at this, and there's always this sort of pressure to go faster in medical imaging, right? Because either monetary or it makes a technology possible that's not possible if it's too slow. All right. So what we said is we go from a fully sampled to undersampled. So this is basically leading to aliasing, right? And this is exactly what we see here. So this turns out to be the minimum norm estimate. Okay. So from a point of view of linear algebra, it's exactly the same. Essentially, it's saying if you don't have enough equations, then there's lots of solutions. And the solution I'm going to give you is the one that has the smallest norm or size. And that turns out to be the alias solution. Okay. So the idea is we want to go faster. So, but somehow we have to get rid of this aliasing. And so the question is, how do you get rid of that aliasing? And this is basically, we use the coils. We basically say, okay, I go from undersampled to oversampled here, where now I've got an overdetermined set of equations. And so now I should have a chance of getting rid of that aliasing, right? Because these coils now, the information I lost by undersampling, these coils now, these coil sensitivity patterns are bringing that information back in because they're telling me something about my object. So that's basically, in this case, for example, we have our oversampling, and then we use the information from multiple coils to now sort of solve for the answer we want. And what we found out, and this is this process is called sense, is it turns out to be lots of little linear equations. So for example, if I want to know the values of these two voxels, okay, if I undersample, they're going to be aliased, right? They're going to be right on top of each other. So unaliasing is saying decoupling them and spreading it apart, okay? And so you can sort of see here, this is the linear equation that really matters. So see every sample, every image I take, let's say F1, let's write it down, F1 is going to be equal to CA1 I1 plus CB1 IA IB. Okay. So the aliasing is saying in my first image, those two things lie on top of each other. Okay. But they're weighted by the coil sensitivities. And the next image, they're also weighted on top of each other, but they're weighted by different coil sensitivities. And so these are just a set of linear equations that I can solve. And so let's look at these. And what we said is it really what matters and what you'll sort of look at in your homework is these are essentially two vectors. Let's call this V1, V2. Okay. So if those two vectors are very similar, then my estimates can be really noisy and not very good. So if the coil sensitivities look very similar across space, it's going to be hard to solve this linear equation in a stable fashion. So what I want to do is I want to pick solutions where the vectors are ideally they're orthogonal, right? In which case I sort of can get my best chance of reducing the noise. Yeah.
Clarify, is F1 and F2 the F vector? Is that what we're measuring and then we're trying to decouple it into IA, IB, or is it?
Yeah, so exactly. So F1 is this image here. Okay. F2 is this image, F3 is this image, F4 is that image. So F1 is the value, is basically the value, what is that point there? Okay, the value of the image there. F2 is this value, F3 is this value, and F4 is that value. So in each of those, basically the original, because it's aliased, there's two things on top of each other. And now we unaliasing and separate them. Does that help? Great. Okay. Okay. So what you'll see in your homeworks and sort of play around with what we talked about last time. So here, so let's call this vector V1 and this is V2, right? And so if you think about these as vectors, they obviously across this dimension, they look pretty different, right? So then when I go to, so I go for my aliased images. So these are aliased, right? And when I go to solve for my answer, I get this image here, which looks pretty good. I've added noise, so it's a fair case. So noise will get amplified. But that looks pretty good. And what we talked about is the way we measure it is something called the G factor. And ideally it's one, and in this case, it's pretty close to one. And so we think, okay, we've done a pretty good job of not amplifying noise. Okay. On the other hand, if you look at this vector and this vector here, the vectors, one is the blue and one is the red, those look pretty similar, right? So essentially in vector space, they have a very small angle between them. And therefore, when I try to come up with my estimate, I get this really noisy estimate, okay? Because basically it's at every voxel, it's not really sure whether it should go to this place or this vector or that vector, okay? And so at every voxel, it doesn't really know, does the energy go to this one or this one? And so it sort of ping pongs between those two alias voxels, right? And that's why you get this really noisy image. Right? So hopefully you guys will get something similar on your homeworks. I think it's more, that last homework problem is more of a guided experience, right? You sort of plug and chug and just comment on what you see, right? Okay, so what we talked about, what we just talked about is this thing here. It's called sense. Okay. And we're not really going to spend, so it turns out that there's sort of an equivalent approach that we could do in the Fourier domain, which is called grappa, right? Which we're not really going to go into too much detail. But these are all basically in the realm of what's called parallel imaging, where we're either using Fourier data or we're using the coil sensitivities to give us a problem that just from the data alone, we're trying to come up with an estimate, okay? So now we're going to switch gears. We're going to say that's okay, but that's really not sort of the best approach. So here's the first step that was taken in sort of about around 2010 or so, which is if I have a 16-bit image, right, which just means that every voxel is represented with 16 bits, or I could have a 32-bit image where every voxel has 32 bits. And let's say I have a 512, 5 by 512 image, right? That means I could have 17 billion possible images or 1 quintillion possible images. All right, so that's a huge space of images I'm trying to solve for, okay? And so what Fourier transform does is it's trying to solve for that entire space. It's saying, I need to figure out, like any solution within that space is okay. And in fact, all these solutions are okay. These are okay solutions, right? But clearly, those don't look like very good medical images, right? If you went to the doctor and you got these images back, you'd ask the radiologist, like, look, can we redo this, right? This is not, I don't want my surgery based on these images, right? So we know that most brains don't have stripes through them or have like weird patterns in them. Okay. So from lots and lots of experience of looking at images, we know that those are not good images. And in fact, we know that the space of biological structures of things that look like brains is much smaller than that overall space. Okay. So we should take advantage of that. We should say, hey, when you're solving this problem, don't give me answers like this. Okay. You should downweight those answers and say, these are unlikely to be, the probability of these being the right answer is very low. So even if so basically so somehow you need to downweight that. So the first way we're going to do it is something called compressed sensing. Let me just show you sort of the idea. Is here's our happy Shep-Logan phantom, and here's its Fourier transform. And here we're just going to downsample. And here it's done randomly, okay? Probably with like Poisson or something. So you can sort of see we've just thrown out lots of data, and we've only from a lot of bright spots, now we have much fewer samples, okay? And if we're just going to go through and do this minimum norm solution that we talked about, we'd get a very bad looking image. So this is obviously, so from this undersampled data to here, that's the traditional route you would take. That's solving the equation, and it's underdetermined, and so the minimum norm solution just gives you something that doesn't look very good, okay? And the idea is if you actually take into account some priors, we'll get to this minimum total variation. We use a convex nonlinear reconstruction, which is called compressed sensing. You get this very good looking image. Okay, so the question is, how does that work? Like, what might be what should this do? So here's the idea. Remember we had this linear equation, the signal equals E times M, right? This is my data. This is my image, and that's my encoding matrix, right? And what I want to do is I want to come up with some estimate M hat. That's my estimated image, right? And one thing it should satisfy is if I take my estimated image, it should reproduce my data. Okay, so that's the error. So if I take whatever estimate I have of my image and I encode it, it should give me my data back, which means that the norm, the size of that error, should be less than some epsilon. Okay, I want a small error. Ideally zero, right? So that's what's called data consistency, right? Because if your estimate going through the encoding matrix doesn't give you your data, then it means somehow you're somewhat ignoring your data, right? So if you're assuming whatever data I have, I think it's okay. So at least give whatever estimate you give me should match my data. Now, one of the estimates that matches is the aliased image, right? The one that looks bad. So we're saying, okay, that's one possible solution, but now we want to impose a constraint, and here's the constraint. We're going to multiply my estimate by some phi, and we're going to say this is going to minimize the L1 norm. Okay. And the idea behind this is that images have a lot of structure to that, right? Like you all have like cell phones and computers and huge TVs, right? Like and so the idea is, it's pretty amazing. Like, does anyone remember? I don't know, you guys are maybe too young. Do any of you remember when Netflix used to send out CD-ROMs or DVDs? Okay. So before Netflix was this huge multi-billion dollar company, Does anyone know what Blockbuster Video is? Okay. So Blockbuster Video used to be like how you would get movies, right? So like it's a Friday night, you're like, "Oh, what do we do?" You go to Blockbuster Video. Like everyone's at Blockbuster Video, and you're getting a VHS cassette, and then at some point it becomes DVDs, right? So you basically are going there. You got to drive your car or walk there and go get it, and they'll be like, and if it's sold out, then you got to go pick another movie, right? Um, so does anyone know what happened to Blockbuster Video? Went out of business, right? Okay. So Netflix, its initial business was to like say, okay, well, that's sort of stupid that you would have to go to like the store. So their key was they just started shipping DVDs to you through the mail, right? And then you could select some and then you'd send them back. And this went on for a while, and everyone's like, oh, this is a stupid business. Like, is it, how's this going to like overturn Blockbuster? But basically, at the same time, they realized that the long game was you got to stream the movies, right? As internet speeds became faster, and broadband became it became actually possible. But even with internet speeds, you're not going to be able to do that unless you compress the data. Okay. Because there's like a movie has a lot of information. So if you send every voxel, every bit over, then that's going to be still too much, right? So like sometimes like, when in the old days when there was like analog TV, when you had a bad signal, it would just look noisy. Okay. Now, like what happens if your internet connection is bad with your TV? What does the image look like? Anybody? Sorry, go ahead.
Stuttered, laggy.
It's laggy, right? Sometimes it's like a little blurry, right? It starts out blurry and then it sort of fills in the details, right? So sometimes like you go to YouTube, right? And you start looking at videos like this is like really blurry, right? And then over time it's like, wow, it got really better, right? So what are they doing? They're basically doing something like what compressed sensing is doing, right? Essentially, instead of sending over all the data, they're just sending over enough coefficients. Typically, so there's JPEG, there's MPEG, there's different compression algorithms. They're all sort of somewhat related to Fourier transforms and wavelets. And the idea is there are certain domains where if I have an image, I have to send a lot of data over. But if I can transform it to another domain, like the wavelet domain, there's not many coefficients that are not noise. Okay. And so that's shown here. Like here's an image here. If you thought about transmitting every voxel, that's going to be a lot of data, right? But if I transform this into the wavelet domain, you can sort of see most of the images is like black. There's nothing to transmit. So I just have to transmit a lot less data. Okay. Another way of saying this is this has a pretty small L1 norm. Okay. L1 norm is sort of, you can think of it as sort of, it's the sum of the absolute values of all the coefficients. And so it's a good proxy for like how many coefficients do you have, right? And so this has a small L1 norm as compared to the image. Okay. So another way of saying is it's sparse. It's a pretty sparse representation. So this is going to enhance sparsity. Okay. So that's my first way. Yeah, go ahead.
How is it different from downstairs?
With downsampling, like if you downsample an image, for example, then like let's say, like in this case, this wavelet transform, it's like I'm getting rid of, say, like 80% of the coefficients, right? What would happen if you got rid of 80% of the voxels in that image? It wouldn't look very good. Right. So it's basically saying you're going to a domain where you're much more efficiently representing the image. Yeah. Um, I mean, it's sort of like I used to have a slide, many years ago where I'll tell you the story and you can tell me if you think it's true or not. Um, so there's this story that like, Eskimos have like 50 words for snow, right? There's like snow that happened after a blizzard, or snow that happened after like, a big rain, or snow that, occurred after 2 days of sun and then rain, right? So the idea is like if you're an like if I tell you it snowed and you ask me what snow was, I'd have to tell you, oh, the snow was like sort of light and fluffy and then it blew like this, right? Whereas the story is if you're an Eskimo, you've already got these words. So I would just say, snow one, and you would know exactly what I meant. So I don't have to transmit as many. words to you, right? Because I've got a prior built up, right? That's like language, right? Like, um, so the idea is there are certain, each word you can think of as what we call, like, there's this term, everyone know what a basis function is? Or like a basis vector? Okay. So essentially, like what we were talking about in Fourier domain is every like sinusoid is a basis vector, right? It's like a part of your alphabet. Okay. It's sort of saying, like my Fourier alphabet is all these sines and cosines, right? My wavelet alphabet would be sort of these sines and cosines that sort of are shaped like this with a window. And so if I pick the right alphabet, then I can represent things much more efficiently. So that's the basic idea, right? Okay, so we choose phi to be a sparsifying transform. And so what we talked about is like there's the wavelet transform. There's also something called the finite difference, the total variation, which is basically like take the derivative of my image. So that happens really well. I'll show you some images where that works really well. And here it is actually. So what we're looking at here we're looking at an image that is somewhat sparse already, right? If you look at an angiogram, this is an angiogram showing the vessels in someone's leg, then, you know, ideally it would just be very sparse. You just have white, you just have bright stuff where there's vessels and black everywhere else. So there is this idea that even in the image domain, this could be a sparse image, right? So one way to go faster, right, is just to acquire less K-space data, and that's a low resolution data. Okay, low resolution. And you can sort of see you're losing some of the details, and some of the vessels are actually disappearing. Like this one here, I don't see it anymore, right? Okay. You could also do your best guess at like a minimum norm solution, you know, or some other linear solution. And as you can sort of see here, it's also losing information. Now, if I do compressed sensing, it's actually pretty good. Okay. And in fact, it's actually getting rid of some of that background and just showing me my vessels, right? Because it's sort of geared towards just showing me stuff that is sparse. It's giving me a sparse image, all right? So this is sparse. Similarly here, these are my fully sampled data, okay? And once again, these are pretty sparse, right? I mean, basically, you just see these are basically showing you the vessels in the brain, okay? And so neuroradiologists, if you've had a stroke or something, and we'll talk about how this works in a future lecture, this is sort of what they'd be looking at, right? They're looking, oh, where are your vessels blocked and how that's doing. And so you can sort of see here, um, here is where they've gone 3 times faster. So they basically got rid of like 2/3 of the data, but by using compressed sensing, it still looks pretty good. And then here they've gone 6 times faster and it still looks really good. Okay, so here's the idea. You can go much faster and your image looks almost just as good, and sometimes even better. Okay, so that's compressed sensing, and that was the first foray into saying we know something about images. One thing we know about images is that they're either sparse in their image domain, like angiograms, or if you take the wavelet transform of them, they'll be sparse in that domain. All right. So now we switch to deep learning, which I'm sure everyone has heard of. And, you know, actually, when we first started talking about deep learning, there was no chat GPT. Okay. So MRI was already starting to do this even before, you know, sort of the public really got, you know, really excited about deep learning. And it wasn't until I guess about 2 years ago that chat GPT really took off. So this predates all the LLMs, but some of the ideas are very similar. Um, so the idea is that, you know, here's my data, right? And instead of going through a Fourier transform, we're going to go through a deep learning network and get my image out. Okay. And how's that going to work? Well, it's basically the idea is in this paper, which was the first paper to sort of really show this, they actually trained it on, it doesn't really show up very well here, but they actually trained this deep learning network on just a lot of just images. So has everyone probably heard of ImageNet, right? It's like this big database, so like ImageNet. So when deep learning sort of became really popular at first, you know, it was just well, ImageNet was one of the main things that made it possible. There's this big, huge data set of just images, images, images. And now with iPhones and everyone taking pictures, right? Now it's possible. So, in fact, you could argue that a lot of deep learning wouldn't have occurred without cell phones, right? Because in the old days, like, um, you take a picture and you have to go develop it. There's no digitized images. And then when cameras came out, it was still like, you'd had to remember to bring your camera. Now that everyone has a camera on their phone, there's like so many images available and videos to be taken. So there's all this training data. And then plus they're uploading all that data. So that makes lots of stuff available where you wouldn't have been able to do that, even just 10 years ago because there wouldn't have been the data to train your stuff. So the idea is they look at all these images and they say, okay, these images exist on what's called a manifold. Okay. And you can just sort of think of a manifold as sort of some subspace of the overall, like we talked about this overall space of images, but then there's some space in that, which is like a subset, which basically represents your images and say, okay, whatever estimate you come up with, it should lie on this manifold because if it's an image, it should lie on this manifold. All right. So that's this surface it should lie on. And so it turns out the code, we're not going to go through the code, but some of the projects might go through it. I mean, it's super like that's all the code, right? I mean, it's literally like 15 lines of code to do this. Okay. And it worked really well. I think when this came out, people were like, at first they're like, no, this can't be true. But then after people started working on it, it's like, okay, well, that's pretty good. So here's the idea. Here we've got if you do encoding where you actually collect radio samples, just like CT, and you and in this case, the reference is like that's the correct image to take. Like that's the base, that's the perfect image. And then AutoMap is the deep learning thing and does really well. Whoops, what's going on here? Yeah, AutoMap here. And then conventional, you can sort of see here was like ART stands for algebraic reconstruction. It's a type of CT recon that people do. And you can sort of see it doesn't really do that well either. Okay. But here's what really makes that sort of cool is like here, if you undersample the Fourier data, then compressed sensing does a pretty good job, but AutoMap does just as good. And here's the key. Compressed sensing can take hours and hours. It can take a long time to reconstruct because you're solving this non-convex problem. Whereas with deep learning, once you have the coefficients, this is what made NVIDIA like $1 trillion company, right? Everything is just like GPU, right? It's just like forward computation, right? It's like that. Okay, so it's super fast to once you have the coefficients, computing that image is very fast. And then here's a really cool thing here where now here, what they did in their simulation is they just sort of took every line and just sort of shifted it a little bit, right? And if you reconstructed that, that gives you lots of really bad artifacts. Okay. But if you give that data to the deep learning, it says, well, it actually sees through this artifact. It says, well, that data is sort of corrupted, but it's telling me something about my image. So I'm going to just find the data, the image that best matches my data, and somehow it basically sees through all those artifacts. Yeah.
Be trained on this line
No,
or
that's the thing. It doesn't have to be trained on it. So that's the thing that really sort of is shocking about thing. It's but you think about it, it makes sense because if you like, if you're an expert in something like I don't know, like if you really know like cars or something, right? I mean, you can just look at a car and say it's this model or it's that or something's wrong with the car, right? Whereas someone not familiar with cars wouldn't be able to tell the difference between like, like a 67 Chevy Ford Mustang and a 68. Like so you already have if you have a lot of knowledge about how things should look, you can sort of put that prior knowledge on. Okay. The other really cool thing is these deep layers here. Let's see. These are convolutional neural networks. Okay. And so there's convolution going on in here. And it turns out that these kernels that they look at, if you look at these kernels, What do they remind you of? They look like Fourier components, right? So without even telling it what Fourier, the model has no idea what Fourier transforms are, but just by training it on all these data, it actually figures out the Fourier components for you. So basically, that final image is just going to be a sum of Fourier-like components. Okay. But the key is it's not going to use the ones that are not like it's not going to sum them in a way that's going to give you artifacts because it knows if I sum it this way, I'm going to get something that's not probable. So it's going to actually use them. It's going to be smarter than a Fourier transform. Yeah.
So is it in a way like being which Fourier needs to be used to sort of best do?
Yeah, it's not only doing that, but it's also summing up in a way that's not going to give you artifacts. And also, as you sort of see, it has something, it's not pure Fourier transform. It's got some weird stuff to it too. So it's sort of like saying it's like Fourier on steroids. It's sort of like this is Fourier tuned to images as opposed to just standard Fourier transforms. Okay.
You like reload all the weights to be just components of Fourier.
You could, but it wouldn't do as well, right?
As in like if you go through the training process and instead of setting the prior to be just random Gaussian noise, set it to be Fourier components.
Um,
Would it
you could, but you would get you I that's a good question. I mean, it's worth checking out. My guess is you probably wouldn't do as because if it's not trained on images, then it would still give you stuff that.
like you train it on images, but instead of initializing with randomness,
Oh,
initialize.
right. Yeah, as part of the training process, yeah, I don't know. The paper might have gone into that. I don't remember the details. Yeah. There's also something I think one of the projects might be also there's a lot of interest in what's called physics-informed deep learning, right? Sort of making sure you put the physics into it. And so that's certainly something that's an interesting area. So that I don't think AutoMap really didn't put any physics per se into it, but that is sort of what people are looking at. So here's a case where AutoMap does really well. Basically, here's the fully sampled ground truth. Here's AutoMap, and then here's if we did sense, and so this is showing the error. So AutoMap's error is much less than the sense error. Okay. Um, and then here it does really well when we add noise. So for example, in this low SNR regime, you can sort of see here that if you just compare, this is AutoMap to conventional imaging, you can sort of see that even when I add noise, it just basically it knows random noise is really not part of what good images look like. So it basically takes all that random noise out. Okay. So obviously, we don't really have time to go into how deep learning works. Some of the projects will probably play around with it, but the idea is that there are different approaches, and I'm just going to go through some just so you sort of get a sense of what people are doing. But you can sort of see things that are being used that you probably have heard about in other classes, like GANs, like general adversarial networks. You've probably heard of maybe UNet and things like that. Okay, so a lot of things that people are using for anything to do with images, then people will tend to use for this. So different approaches you can take is you could actually take your data, right? And you could do the inverse Fourier transform and come up with, say, like an aliased image, right? And then you could ask your deep network, okay, just correct this for me. All right. So you could sort of do that. Or you could do what AutoMap does and say, go directly from the data to cleaned up data and then do the inverse Fourier transform and then and give me my image. Or you could do directly, this is what AutoMap does, just go from case space to image. Or you could even do a hybrid approach where you could sort of say, let the Fourier transform do some of the lifting, right? But also try to figure out what the correction is directly from the case-based data, and also, and then also clean up your image a little bit with a deep network. So people have played around with all these different architectures. I'm not saying what is better or worse. I'm just saying that there are people are still playing around with what works best. But here's the real interesting thing about it, which is that this is why deep learning is such a big possible win, which is it reduces your imaging time and also the reconstruction time is very short. Okay. Whereas with compressed sensing, it reduces your imaging time, but sometimes the reconstruction can take too long. And that can be a problem if you're like scanning lots of people, right? Because then like what happens is sometimes the scanner is just like if it doesn't have enough GPUs, it's just sort of stuck there reconstructing and it can't be used for the next patient yet. All right. Obviously, the manufacturers sort of try to get better GPUs all the time, but that's one of the things where there has been sort of there's still compressed sensing out there, but I think there is a real desire to go toward more deep learning. And just to remind you, what it's doing is remember we have this undersampled set of equations. And so all of these are possible solutions, right? Okay, including not very good looking images, right? So what it's trying to do is it's trying to say, okay, for all the possible solutions, this is the norm estimate, give me the solution that is sort of lies on my image manifold, that best agrees with my prior. And so that's sort of shown here where I'm trying to get a sort of, this is representing my manifold. I'm trying to get an image that lies on where I think images should lie. Okay, so that's the basic idea. There's some nice textbooks out on there if you want it. But now let's talk about some of the caveats and why some of like my colleagues who are radiologists are very skeptical of deep learning and why, in some cases they're very cautious about it. So this is the ground truth. This was a paper that came out in 2020. Um, and this is the reconstruction. And these are just examples that are highlighted where essentially the deep learning put in something into the image that wasn't there. Okay, so you've all heard about hallucinations. Well, so basically it's just coming with its best guess. So the image it comes up with looks like could be possible. But here's the case in a diagnostic setting, you know, if it puts in like a spot where that could be a spot and it looks very realistic, that's a problem because now the radiologists go, well, is that a real spot or is that a hallucination? Okay. So here's an example here where it's probably not a bad thing because this thing it doesn't really look too biological. So but it did put that in there and it looks okay. I mean, if you were to look at that, you might say, well, maybe there's something there. And radiologists see so many images that they may rule that as an artifact. But let's say you're not a very experienced radiologist or you're working someplace in a community hospital and you're seeing so many cases a day, you may not have enough experience to know that that's an artifact. Okay. Here in this case, you can sort of see here, it injected this part here where nothing existed. And this was a really interesting example here. See this thing here? It's not in the original image, right? And actually it looks a little weird. I mean, having looked at a lot of brain things, I'm like, what? That looks a little weird to me. But it matches this, and then it just adds on something like that, right? To the original image. So if you have enough experience, you could probably read through these artifacts, but that's the danger. So I think people are sort of proceeding with caution because until people have enough experience with AI, they still have to be sort of concerned with these artifacts. Okay. So that's where we are today. But I don't think deep learning is not going away. It's just people are going to come up with better ways of doing it. All right. And this is just showing some additional images, just showing that, um, deep learning does pretty well. Okay, so we're going to stop there on terms of the recon. And so are there any questions before we sort of switch gears into, we're going to start revisiting relaxation and getting into sort of, what is it? And then how do we actually use it to make images? Okay. Okay, so this really begins sort of more of the applications part of the MRI treatment. So just to remind you, when we talked about relaxation, there's two main things you need to remember. There's T1 and T2. Okay, T1 governs how quickly we go back to M sub Z for the longitudinal component, and then T2 means the return to equilibrium of MXY, which is going back to zero, and this is going back to M sub zero. Okay. So those are the return to equilibrium. And what we saw before is that typically the transverse component dies off much more quickly then the longitudinal component returns. Okay, so that gives you this sort of picture where we start off in the transverse plane, we sort of do this very quick death spiral, and in the meantime, there's some regrowth of this component. Okay. And then there's different T1 values, which we're going to take advantage of to create image contrast. And basically, we want to talk about the first thing is dipole-dipole interactions, and we're looking at the T1 relaxation time. Okay. So the idea is if I have remember when we had the magnetization like this, and we sort of we gave it an RF excitation at the Larmor frequency to tip it away, right? Okay. Now, it turns out that this can go back to here, but the process is pretty slow, except for the fact that if you can help it by giving it some energy at that frequency to sort of whatever frequency that tips it away will also help get it back up to here, okay? So that's where these dipole to dipole interactions occur. And so the way it occurs with the molecules is every little proton is like its own little magnet, right? Remember, it's a little dipole, right? So if you have these things that are moving at the right frequency, then they can help return the magnetization back to its equilibrium. Okay. So that means that there's like a sweet spot. So that's related to the tumbling rate. Okay. If the tumbling rate is too fast, right? The frequency is not at the right it's not the right frequency. The tumbling rate is too slow, it's not at the right frequency. When it's just right, when it's at the Larmor frequency, then it can sort of do this stimulated relaxation. Okay. And this was actually something that I think Einstein was one of the people to help figure this out. Like, why is, how does this help with the return to relaxation? It turns out if this didn't happen, it would take a long time for the relaxation to occur. Yes, question.
So the context of just how T happens.
Yeah, we're talking about how T1, why, what are the factors that lead to T1 and sort of so basically the main thing I want you to get is that it depends on the molecular tumbling rate. Okay, so anything that gets that tumbling rate into the right frequency range will help you have a shorter T1. Okay, so this is basically the T1. So when you've got the right tumbling rate, the T1 is at its lowest, and then if you go away from the right tumbling rate, it sort of increases. Okay, it's still going to recover, but it's going to recover much more slowly. So that's shown here, where this is sort of Goldilocks is shown here, Goldilocks and the three bears. And essentially, the most efficient T1 relaxation occurs when the tumbling rate is close to the Larmor frequency. Yes, question.
Also both the other types of MRI, or is this like a hydrogen specific thing because water is weird?
It's applicable to any other MRI because it's basically just based on any precession. Yeah. Okay, so that's the T1 curve. So it's got sort of this shape here. It's got a clear valley to it. Okay. And so one of the effects of that is if I have a certainly tumbling rate, right? And so here, let's say my Larmor frequency is here, right? And there's a lot of water that's bound, and typically bound water will have the right tumbling rate. Okay. But now let's say I go to a higher field strength. Okay. Like I go from 3 Tesla to like 10 Tesla. Now my frequency has increased and it's gotten place where there's not that many molecules tumbling at that rate. And so that's actually one of the problems with going to higher field is you get a lot of SNR, but things take so long to recover to equilibrium that there's a trade-off. Okay. The other thing that helps that typically has very short T1s are things like fats and oils, right? A lot of the stuff you're going to consume over the Thanksgiving holiday, right? Those tend to have a short T1 because those bound hydrogen protons, just because of how they rotate, just turn to have, at least for the field strengths we're using, tend to have the right tumbling rate. Okay. And the other thing we'll talk about is T2. So that's the relaxation. Remember, T2 is basically the transverse relaxation of the spins. Okay. And let's review why that happens. So remember when we talk about K-space, we assume like, let's say in a volume, let's say we have lots of spins, like each of my fingers represents a spin, they all flip over at the same time. So they're all in phase. Okay. But over time, they get out of phase. And so if you think about the vector sum of these, it's much greater than the vector sum of these, right? And in the limit, once I have a circle of vectors pointing in all directions, in the limit it goes to zero. So when they randomly dephase, I'm going to get back to zero. And that's shown here where you see all the vectors lined up, and then over time, they get out of phase. All right. So the question is, how do they get out of phase? Like what causes them to get out of phase with each other? So once again, every proton is its own magnet, right? So not only does, so let's say there's a spin here and there's a spin here. Not only does this spin feel the main field, but it feels all the little spins here, okay? And so the idea is that as this spin is tumbling, the field it feels from here, it changes the field that this spin feels. So this might go a little faster or a little slower depending on what it feels from this other spin. Okay. But imagine I have this spin is tumbling like in all directions super fast, right? So what's the net field that this guy's going to feel if this is tumbling super fast? It's going to average out, right? It's going to be like zero, right? Because sometimes it feels a field this way, this way, this way. So the faster this one spins, then this almost doesn't feel, all the spins feel the same thing. Everything averages out to zero. And so when the tumbling is really fast, the T2 is very long. Okay. Because essentially I'm here, essentially, it's sort of like if like, you had a whole bunch of people going around, sort of um, surrounding you, and they randomly say turn clockwise, turn counterclockwise, right? If they say that really fast, then it's averaged out to like you're not going to turn at all. Okay, so that's like a very fast tumbling rate. On the other hand, if over the course of the experiment, like they only say fast or slow once or twice, right? Then on average, there might be a net you might have turned, or you might have turned clockwise or counterclockwise, right? So over the course of the experiment, there might be there's no averaging out of what they're doing. And so the T2 tends to have this characteristic where it's very long T2 if things are tumbling really fast, like for water. So this is like water. And then it's very short for things where the protons can't really move around that much. So then each proton can affect its neighbors much more. And this would happen for something like in bone, which is a super short T2. Okay. So here we sort of looking at some of those things. So let's see if this makes sense. We can see sort of for the T2 of water, it's really long. For brain and muscle, it's, this is all in milliseconds. It's on the order of 100 milliseconds. If I look at ice, it's super short, like 1 microsecond. Okay. Because the molecules in ice are not, the protons aren't really sort of moving around. And in proteins, it's fairly short as well. Okay. Okay, so let's think about this sort of to sort of consolidate your understanding is, so imagine I have a vial of liquid and the T1 is 1,000, the T2 is 1,000. Okay. So then I go ahead and add some gelatin to the vial and I let it sort of set. And then I go back and measure it again. What would be a reasonable value for the T1 and T2 of the new mixture? Okay, so I'll open up the poll so people can do that. Let's see. People want to respond online. Okay, so we've added gel. So is the tumbling rate going to go up or down? It's going to go down, right? So we're assuming that, things aren't going to be moved. So we know that T2 probably has to go down, right? So therefore, I guess this can't be correct, right? Okay. The other thing we can rule out is we know that T2 always has to be less than or equal to T1. Okay. So we can rule this one out, right? And we can rule this one out too, right? Okay. So now we're just left with, and we know T2 doesn't stay the same, so we can rule this one out, right? So now we're just left with these two guys, right? So for both of those, T2 went down. So, okay, that seems reasonable. All right. What about T1? In one case, it went to 500. In another case, it went to 1200. Okay. So in this case, what's more likely? Did it go up or down, right? Remember we have this curve here, right, of T1, right? So what do you guys think? It went up? Okay. So here's the tumbling rate. So we know the tumbling rate went down, right? So if we were here, we could end up going this way, right? Okay. But if for some reason we'd been up here, maybe it could have gone down as well, right? So it's sort of without more information, it's hard to say. You could argue that, well, if this was water and it had long T1 and it was already near the sweet spot, then probably it does go up. So all things being equal, it probably went up, but you could imagine cases where, if I didn't really tell you where the liquid was, so maybe it could have gone down. But yeah, I would say I agree that probably all things being equal, probably E is probably more likely. Okay. All right, so that's all we're going to talk about for T1 and T2s. And then the next thing we're talking about, which is sort of a really interesting part of MR, and it's going to lead to functional MRI. And then so the two things we're going to really be leading up to are understanding the spin echo, which is like a bread and butter, and then functional MRI. So that's what this is going to lead to. Okay. So here's a really important thing. So typically we spend like for these high field magnets, like a 3 Tesla magnet, you'll spend for the system itself, it's like, $2 to $3 million. And a big part of that cost is the magnet, right? And we create these magnets that have really uniform fields, right? We assume that the B0 field is uniform, right? In all our assumptions. But here's the interesting thing, no matter how much money you spend on the magnet, once you put something in that's biological, it's going to perturb the field and make it non-uniform. Okay, and that's what we want to look at. Well, what happens there, and what can we do about it? So why does that happen? Well, so let's say I have this uniform magnetic field. Okay, so I've got this beautiful magnetic field that I've set up. It's perfectly uniform, and now I come in and I put in my object in. And as you probably remember from your physics courses, there can be paraferromagnetic materials that will tend to concentrate the field, right? So now all of a sudden the field is going to sort of be focused into my object, or there can be diamagnetic things that tend to repel the field. Okay. So essentially, a measure of that is susceptibility. So what we're saying is different tissues have different susceptibilities. Okay. So like water, fat, calcium tend to be diamagnetic. Um, but things like iron and tend to be obviously ferromagnetic, and then paramagnetic. Okay. And then also we have things like ferritin in them. So there's all these things that we have in our body. So clearly we have a lot of water in our body, but as we'll find out later, there's also iron in our body. Okay. And obviously other molecules as well. So here's the thing. So here I just have, these are my sort of my standard images. And here what I'm showing is a field map. Okay. And what it's showing is like the bright is maybe like 0 hertz and the dark is like it's saying this is sort of a map of the Larmor frequency. Okay. It's sort of saying, and remember the Larmor frequencies It depends on the field strength, right? So if the field strength is lower, then I'd have a lower frequency. So lower frequency, right? So you notice this is an image of someone's head. Their head looks normal, right? This looks like a normal looking head, right? But yet when I look at the fields in that head, I have this really big dark spot at the front of the head. Okay. So what do you think is causing that dark spot? Like what do you have at the front of your head that is sort of different in material property than the rest of your head? Anyone? Yeah, you've got your eyeballs, right? You've also got your nose, and what else? Does anyone know what a sinus is? Anyone ever have like a sinus infection or a cold? So you have these big air pockets here, all around here, and these have a different susceptibility than the surrounding tissue, and so that interface is what's causing all this sort of this dropout, okay, or change in the field. Okay, so what that means is these spins here close to that interface are going to process at a different frequency than the spins elsewhere in the brain, right? Because they have a different lawnmower frequency. It's experiencing a different field. Yeah, question.
Collect these.
Oh, how do you collect these? Um, it's a good question. There's something called a field map acquisition where we actually acquire the data at two different echo times, and then we look at the phase that's accumulated. So it's basically, you know, we sort of see if it's zero phase, right, then if there's no added frequency, then a spin will stay here, right? But if there's any change, we can measure the phase. So we basically just measure the phase of the spin. And the phase of the spin tells us how much frequency offset there was. Yeah. So that's a good question. So that's for sort of a very practical application of understanding phase. Okay. So yeah, so the field map is basically we measure the phase of the spin and then we convert that into a delta frequency estimate. Okay. Okay. And so here's the idea why this is important. So here we're looking at all these spins are aligned, okay? And this will be the fundamental idea behind functional MRI as well. And so imagine that I put these spins sort of around this guy here, right? And the colors are just saying that they have slightly different field strengths, right? The red is higher, the blue is lower, okay? And so what's going to happen is those spins are going to get out of phase, right? And there's some dephasing there. And so then the overall vector sum goes from here to here. So there's a decrease in the signal due to dephasing, right? Now, if I make the field inhomogeneous even more, now the spins experience much different fields, right? So over the same amount of time, at some echo time, they're going to dephase even more. Okay, so the more inhomogeneity there is, the more dephasing, and the more the MR signal is going to go down. Right. And the way we're going to represent that is we're going to add this T2 prime term to the our T2. So T2 is the random dephasing we talked about. This is now representing the static dephasing. Right? And so the overall thing is what we call T2 star. That's the effective T2, and it's given by 1 over T2, which is the random dephasing, and this T2 prime, which is the static. And here's the really interesting part. T2 is due to random motion, so there's really nothing you can do about it, right? It's just nature. Just like whatever happened, happened, right? But T2 prime happened, you can actually estimate what caused T2 prime. Therefore, you should be able to fix it and reverse it. Okay, so we'll talk about one way of doing that, which is the spin echo, which is like one of the most famous discoveries in MR, or NMR actually. Um, so typically, and later on we're going to talk about gradient echo sequences. So this is something that you'll hear about in MR. So these exhibit what's called T2 star decay because they are sensitive to all the decay that occurs, whether it's T2 or T2 prime. We lump everything together. And so the idea is if I have, let's say my object was erect, right? I know the Fourier transform is going to be a sinc function, right? So if I had no decay, I would just get that sinc function, right? But things are decaying, so I represented it as that sinc function multiplied by this weighting term. Okay, so I have that T2 star. So basically, as I'm collecting the data, it's being reduced by this weighting term that's decaying at T2 star. All right. So this is what we call anything related to these types of effects are called susceptibility artifacts. So sort of here you can sort of see someone you're seeing a picture of their femur, and there's like two really dark spots in their femur, right? So what do you think is going on here with this person? Do they actually have holes in their thigh bone? Yes or no? Probably not. Okay, so what could cause that? Yeah, they probably have some implants, right? They probably had some surgery and they probably have some metal in there that's causing the fields around it to be out of phase. Okay. What about this poor person on the right here who's missing a mouth? Okay. So what should we do about this person? So first of all, do we think that person is actually missing their mouth? No. Okay. So what could cause this artifact? Yeah. The what? The air in the mouth. Okay, that's one thing. But we all get MRIs done all the time, right? And yeah, go ahead. Braces, yeah. So this person has metal braces or something in their mouth that's perturbing the fields enough. There is obviously air, but when you close your mouth, it's not so bad, right? So but yeah, this person is fine. It's just that they should never have been scanned in an MRI, okay? Because typically one of the contraindications is, anything metal in you. Um, it even turned out that, like sometimes people have tattoos that have metal in them, right? That can actually perturb the field. It's also a safety issue because any metal can absorb the radio frequency pulses and actually heat up, and actually burn the subject. So we basically have to be very careful about anything that's sort of metal or metallic in the MRI system. Okay. So the good news is, oh, and so here's so another theme of MRI that's sort of a good thing to think about, and it's actually good for your career is oftentimes something that's really bad for one thing is really good for something else. So if you go through MRI and look at techniques that are used, oftentimes they're like, oh, there's a problem with my image, right? And people try to correct that problem. But then like 10 years later, someone says, oh, this is great. I can use that to image something else, right? This problem becomes a solution. So here's an example, which is called susceptibility weighted imaging. And this is what it looks like here. So what does that image look like here? What's dark in that image? Yeah, go ahead. Yeah, all the vessels. Okay. So what would make all those vessels dark? Yeah. Yeah, exactly. So basically this is actually a venogram. It's actually measuring not all the vessels, but just the ones that have a lot of iron, which, as we'll talk about when we talk about functional MRI, is the veins, right? So everyone knows that you probably heard about like oxyhemoglobin and deoxyhemoglobin and hemoglobin. So it turns out you have a lot of iron. And so, for example, people who are like anemic have to take iron supplements, right? So essentially that iron is exposed in your veins. And therefore, this technique, which is actually used a lot for like traumatic brain injury, like if you go get a concussion, you'll probably have one of these images done on you because they're going to be looking for bleeding. Yeah.
Titanium blueprint plant, so
Yeah.
if that cause.
Titanium is fine. Yeah, because there's like an MRI safe implant. Yeah. There's typically when you get an implant, it's usually a good idea to sort of get the documentation and to make sure it's MRI safe. So then if you ever have to have an MRI done, you actually have that documentation. Otherwise, sometimes they have to look it up. But if it's titanium, it's usually fine. Yeah. Okay, so this is an example where something that was an artifact in the previous slide is now the source of information. Okay. Now, for a lot of cases, though, we want to somehow reverse that artifact, and that's where the spin echo comes in. And it's actually a pretty simple idea, but person who first thought of it, obviously it wasn't simple until he thought of it, which is essentially, remember I have my spins like here, right? And then they spread out and dephase, right? So then the spin echo says, well, you let some time for them to dephase. Now just apply an R pulse to flip them. Okay. And then this guy, let's say, went faster, this guy went slower, right? And this guy stayed at the isocenter at the same rate. So they dephase. If I flip them, now this guy's faster, this guy's slower. So this guy will catch up and this guy will slow down. And at some point, they'll be back in phase again. Okay. So essentially, the way you can think about it is if you have like a race, right? And you let people run for like a minute, one guy's at the front, one guy's at the back. And then you put the guy at the back, at the front in the back, and the guy at the back in the front, and you'll have them race another minute. So one in the fast guy will catch up, and the slow guy will go back to the mean, and then everyone will be in sync at the end. Okay, so that's all the spin echo is doing, right? So it can refocus that static homogeneity. It can't deal with the T2 because that was random, right? So here's a movie showing you what that looks like. It's basically the dephase, and then we apply this refocusing pulse, and then everything rephases. Okay. So then what we say is that this exponential decay now is only dependent on T2 at the center, right? And so that's the sort of, we call this a T2 weighted sort of sequence, right? Because the spin echo is a 180-degree pulse because it flips things 180 degrees. And we wait some amount of time, tau, for the spins to dephase, and then we wait the same amount of time, tau, for them to rephase, okay? And then we collect our image at the point where they rephase, okay? At least this is where we acquire the center of K space, so center of K space. Okay, so here's what it looks like. If I don't do the spin echo, and in this case, we've applied some inhomogeneities, I get these really clear dropouts, right? This a lot of spin dephasing happening there, okay? So I leave everything the same, and all I do is now I acquire the image with a spin echo, and you can sort of see it looks almost perfect, okay? So that's sort of a laboratory demonstration, but that's why when you go to your clinic and if you look at the scans they take on you, you'll probably notice a lot of them have like you might set like FSE, like fast spin echo, or SC for spin echo. Like sometimes when you get the or you can when you get your MRI images back, you can sort of look, there'll be like things that will say, FOV and things like that. And you can generally you'll say what the name of the sequence was as well. And so you'll notice that at least probably half of them are going to be at least spin echoes. Okay. Okay. So just to remind you, we're going to start off. I'm just going to introduce the idea of image contrast and then we'll end for today. Um, so what we talked about is we have either T2 star decay or T2 decay. Okay. So T2 star would be gradient echo. And then this would be spin echo. Okay. And in both cases, we also have the T1 recovery. Okay. So these are the three things that we have going on. And the other thing we have going on is what's called proton density, which is basically, how many protons are there. So now what we want to talk about is we're going to start talking about image contrast. And so for the rest of this course now, we're going to be talking about information, right? Like image contrast. We're going to talk about basic image contrast, then we're going to talk about functional MRI, then we're going to talk about diffusion, looking at flow. Basically, how do we start measuring physiological quantities with MRI? Okay. So the idea is that different tissues do have different relaxation rates. They have different T1s, different T2s, different T2 stars. Okay. In addition, they have different density of protons. Okay. So the thing about MRI is we have a lot of knobs we can turn. Like it's infinite number of knobs. Okay. So we're not going to talk about them all in this course. So we're just going to talk about two knobs, the two most basic knobs that you can change. And one is called changing the echo time. The other is called changing the repetition time. TE and TR. All right. So this is going to be related to T1, and this is going to be related to T2 and T2 star. Right. So that's where we're going. All right. And then in some of the projects will get into other knobs that you can sort of play with to emphasize different things. All right. Okay. So what we're going to do is what's called a saturation recovery sequence. And it's basically we apply a 90-degree pulse and we collect one line of K-space, right? And the idea is we collect the center of K-space at the center of the readout, where we're at Kx equals 0. Okay, so we just keep doing that. We're always acquiring the center of K-space at Kx equals 0, and then in the meantime, we can monkey with the phasing code gradients, right, to collect different lines along Ky. But for today, we're just going to really look at what's the weighting of that. So we know that the longitudinal, the intensity of the image we acquire, if it's gradient echo, there's always going to be this T1 recovery, right? Okay. So basically, the idea is I start off with some magnetization M sub 0, right? And if I tip it all 90-degree pulse, it starts off at 0. So that MZ is going to recover at some rate, right? How much it recovers is given by that equation there, okay? Because if I don't let it recover very much, the next time I come with a 90-degree pulse, there's much less to tip, right? So allowing it to recover tells me how much magnetization I have to work with. And then that magnetization that I tip over dephases, okay? So this would be gradient echo. And I could also acquire a spin echo where I introduce these 180-degree pulses. And now this T1 recovery is the same. This now all I've done is now change that T2 star becomes a T2. Okay, so that's the only thing that's changed. So now let's look. What happens if I make TE very, very short compared to either T2 or T2 star? Okay, then this term here goes away, right? Because e to the 0 is equal to 1, right? So I have, if TE is equal to 0, and I have e to the minus TE over T2 or T2 star, I just basically have e to the 0. And all I need is for TE to be very short compared to T2 or T2 star. So then that's equal to 1, okay? So you can sort of see here now, I've got this density weighting, which I can't really do much in this case, but I also have this T1 weighting, okay? So here's to just get the idea behind T1 weighted contrast. Essentially, if I have a very short T1, then things recover very fast. And so my magnetization recovers quite a lot. And so I have a lot of magnetization to tip here. So I go from here to here, I tip it. Whereas if I have a very slow recovery, then I have much less magnetization to tip over the next time. Okay. So short T1s recover very quickly, long T1s recover very slowly. Okay. So what this means is that if I look at the T1 contrast, this has a T1 of 800 milliseconds. This is a T1 of 1200 milliseconds. And you can sort of see the green curve records a little more slowly than the blue curve, right? Because a lot longer T1. Now, if I take the difference of those two images, this is the difference, right? I notice that difference is maximized around TR of 1000, okay? And so sort of good rule of thumb is that if I have two tissues with different T1s, like 800 and 1200, all things being equal, like proton density being equal, then, you know, somewhere in between those T1s is going to be the one that gives you the most contrast. Okay. So I think we're at the end of our time now. So we'll pick up with relaxation again on Wednesday. In the meantime, if you have any questions, feel free to email me or come talk to me after the lecture. Otherwise, we'll hopefully see some of you on Wednesday, and also keep an eye out for feedback on your. We'll probably release the feedback on the proposals um, by definitely by Wednesday. And so then if you're asked to submit a revision, just try to do that by, like, the end of the week or Monday or whatever. We're just remember the feedback is really to help you get your project in a regime where if you execute well, you should, the scoring should reflect that. I'm trying to help people avoid doing projects where they might put a lot of effort into it, but then the scoring may not reflect well. Okay. So, unless any other questions, let me know. All right. All right. See you next time.